Good evening. Welcome to the last week of class. I wish you could be here. Today, I just want to do review problems. I think we've covered the material for the course pretty well. Some of you are probably wondering about the final. There's some practice problems on D2L. Take a look at those. I put them up here, the first part of them. And the homework for the last two sections we just did when we went back, we covered some of the things we'd somewhat skipped over before. Section 6.4 and 6.6. All right. That'll be it. Problems similar to the practice problems. That doesn't mean that they'll be the same. I can give you disks around the y-axis instead of disks around the x-axis, or certainly different numbers and figures and all that sort of thing. But I'll try to make everything pretty similar either the practice problems or something that's on the homework out of these two sections. These are less important because they're I skipped them in the first place because they're less important. So make sure you do the practice problems on D2L first. And we'll continue doing these next time. We can field some more homework questions if you have any of those also. But that'll be all for this week. I think we've covered the material pretty well. Calculus 2 is a little better than some of the other ones. We have more time to finish. So despite the time off here from the ice storm, we managed to finish the material. Calculus 3 is another story. That's the hardest one to finish. So it'll be a whirlwind next semester if you take it. Any particular questions that you'd like to look at? Follow as I go. I'll go ahead and do some of these just to get them started. It's a lot of stuff throughout the semester. And this will hopefully give you a feel tonight for what we're going to have on the final exam. I want to make the final exam not too long. For one reason, it takes me so long to grade these things. I don't think I can make it any longer than the midterms and get them finished by the time I have to turn the grades in. So the final exam will just be like an hour and a quarter exam. That should give you plenty of time to check your answers and make sure you got everything right. And it'll be based on those problems. All right, here's the first problem off the practice set. Suppose I want to find the volume of the solid that results when this shaded region is revolved around the x-axis. So I revolve it around this way. What do I get? I get sort of a bullet shape, right? So here's the problem. Y equals square root 4 minus x. That's a parabola. Comes down, and by plugging in x equals 4, by plugging in y equals 0, I find x equals 4. So it goes through this point here, 4, 0, just by plugging in y equals 0 and solving for x. Now I'm going to revolve it this way. There's the bullet. And ask, what is the volume? All right. The trick on these problems here is to recognize this is a solid of revolution. What methods do I have for this? I have a method of disks, the method of washers, and the method of cylinders. Any one of those you want to apply is fine. I might give you a hint on the test and say, try this one, but I don't think I'll restrict you. If you think another one works better, you can do it. If I use washers, however, that's a region with a hole in the middle. This doesn't have a hole in the middle. So it's either disks or cylinders. And what you do in both cases, you draw the typical disk or the typical cylinder. Let me use disks. I think that's the easier of the two methods. So here's the typical disk at x. And I notice now that the cross-sectional disks go from x equals 0 to x equals 4. Now I've drawn a nice picture. And what is the volume of that? Well, we call it the volume of a solid of revolution using disks. Is just to integrate the cross-sectional area pi r squared, where r is the height of the function. So pi f of x squared dx, from the min x to the max x goes from 0 to 4. Then you just have an easy calculus 1 integral to the right? The pi comes out. Integral 0 to 4 f of x is square root of 4 minus x. Since that's squared, nicely we have a very easy integrand. We just have to evaluate integral from 0 to 4 of 4 minus x dx. Well, integral of 4 is 4x. Integral of minus x is minus x squared over 2. I just need to plug in 4 and 0 and take the difference. So it's pi times, putting 4 here, I get 16. Putting 4 here, I get 8. So 16 minus 8 at the top endpoint minus 0 minus 0 at the bottom endpoint. This comes out to be 8 pi. Hopefully that's what it says on the sheet. Answers are, you can look up on the back as we go and catch me. Any questions on that one? Is it all visible on the board? Maybe I should zoom this in just a little, huh? Okay, so that's the first one. Let's look at the second one. Find the exact arc length of a curve. So we got all these neat applications. Finding volumes of solids of revolution, finding arc lengths of curves, finding a few other things. Similarly, surface area of a revolution. Let's try this. What is the arc length? How much chord I need? If the chord moves along the curve, y equals x to the 3 halves minus 1 from x equals 0 to x equals 4. I'm a fan of drawing pictures on these, although you don't have to on this one. X to the 3 halves is somewhere between x to the first and x to the second. So it looks kind of between a parabola and a straight line. Here's y equals x. Here's y equals x squared. Y equals x to the 3 halves goes kind of in between like that. And maybe I should draw more of it though, since I go to x equals 4. And now let's see, 4 to the 3 halves is, well, square root of 4 is 2 and cubed is 8. So it goes up to here, 8. What is the arc length? Well, this is a matter of memorizing the formula, although I think it really behooves you to know the proof. Sometimes the proof helps you remember the formula. The arc length of a curve, a smooth curve, is integral from the beginning point to the end point of the square root of 1 plus f prime of x squared dx. Maybe you remember the proof of that was by taking a whole bunch of little line segments here and taking the limit. And so this is the root sum square of the x and y increments times dx. Anyway, so this was the formula we came up with, where this is the beginning value of x, and this is the ending value of x. And I might give you x as a function of y and ask you to do it that way. You just have to turn the formula and integrate 1 plus f prime of y squared dy from c to d. Right? So you can do this along either axis. That's fair game for the test. This one goes from x equals 0 out to x equals 4, treating y as a function of x. Square root of 1 plus derivative of x to the 3 halves is 3 halves x to the 1 half. We've seen this problem before, squared dx. So this is integral from 0 to 4, square root of 1 plus 9/4 x. How do I do that one? This is where one of the things you want to get out of the course is the ability to do a lot of these integrals that come up in practice. Recognize what to do. It really solidifies your calculus 1 ability, right? If I have a function of a function, one thing I should think of is, what if I let u be the inside function and then it's square root of u instead of square root of a mass, I like to say. 1 plus 9/4 x. In that case, du has to be du dx dx. To replace dx in here is, let's see, 9/4 dx. Well, I don't have a 9/4 dx. But I can make it so, right? I can multiply by 4/9 and say 4/9 du to replace the dx that I have there. So substitution, I replace dx with 4/9 du. I replace the argument of the square root with u. And I have integral square root u, or let's write it as u to the 1 half, times 4/9 du. And it doesn't go from 0 to 4 anymore. If you write 0 to 4, I understand you're going to put back x when you're done. But I'll probably make a nasty mark on your paper because technically this is supposed to go from u of 0 to u of 4 if I switch to the endpoints. Well, let's see. U is 1 plus 9/4 x. When x equals 0, u equals 1. So u of 0 is 1. And when I put in x equals 4, I get 1 plus 9/4 4 makes 10. So this now goes from 1 to 10. Well, integral of u to the 1/2 is u to the 3/2 over 3/2 or 2/3 u to the 3/2. The 4/9 comes out of the integral. And then I need to evaluate the integral at u equals 1 and u equals 10, or else convert it back to x and put in 4 and 0, either way. So let's see, it's 8/27 times 10 to the 3/2 minus 1 to the 3/2 is just 1. There's my answer. You can simplify this a little bit. I think this answer is okay. If you write this as 10 square root 10, maybe that's nicer in some ways. This is fine like this. So there's number 2. Any questions on that one? Anybody wants to ask? If you get an arc length problem, just memorize this formula in both the x and y directions, and you can calculate it with that. On the surface area, that was another one. By the way, I wanted to mention that a lot of times people call this ds, and so this is just a common notation. It's integral from a to b ds. Where little s is the arc length. With that in mind, it makes the surface integral a little easier to remember. Here's number 3 application. Find surface area of a surface of revolution revolving y equals square root 9 minus x squared for x between 0 and 1 about the x-axis. Maybe in the test I'll revolve it around the other axis. Well, the surface area has a formula. It just says you integrate from the min x to the max x. Uh, 2 pi radius, 2 pi f of x, ds, where ds is what we had in the last thing. So you're integrating along the arc length, 2 pi times the radius, and that gives you the surface area of the surface of revolution. So this one is square root of 1 plus f prime squared dx. That means when I have to evaluate for this one, well, wait a minute, x runs from 0 to 1. It really helps to sketch these, I said. Let's sketch it. X and y. What does the sketch of this look like? This one, a lot of these you can figure out. If you have a square root, the idea is to square both sides and see if you can recognize it. If I square both sides, it's y squared equals 9 minus x squared. All right. I'll say these are equivalent. If I also, right, this radical means the non-negative number that has a square. So if I also require y greater than or equal to 0, then these are equivalent. Squaring both sides has introduced new negative solutions for y that weren't here, so I have to put that in. All right. Now, add x squared over to each side. I've got x squared plus y squared equals 9, subject to y greater than or equal to 0. I know what that is. That's a semicircle, right? This is the circle of radius 3. X squared plus y squared equals 3 squared. And if I just take y greater than or equal to 0, it's half the circle. So here's the circle of radius 3. But I'm only taking the portion between x equals 0 and x equals 1. So I'll go out to here and take this piece of the circle of radius 3. And then the idea is I revolve it around the x-axis, so it looks like this. It's a slice out of a sphere, right? If I took the whole semicircle and revolved it, I get the sphere. Here's a slice. Right? Maybe that's how I cut my orange or something. How much volume is in there, or how much, in this case, surface area, how much peeling is along the edge is what we're finding. For an orange of radius 3 inches, or like a grapefruit. Well, I went from x equals 0 to x equals 1. All right. 2 pi. F of x is the radius of this thing. So if the idea is to do this at an arbitrary point x, the radius is f of x equals square root 9 minus x squared. So it's 2 pi square root 9 minus x squared, and then square root of 1 plus f prime squared. Well, 1 plus the derivative of this, if I think of this as 9 minus x squared to the 1/2, is 1/2 the same to the minus 1/2 times the derivative of 9 minus x squared is minus 2x. So I'll apply the chain rule. See, this is where you get real good at this stuff in calculus 2. Hopefully, next semester you'll be expert integration. We did a lot of integration techniques this semester, didn't we? And then dx, and this is squared. So 1 plus, here's f prime squared dx, square root dx. So it's integral. I can pull the 2 pi out. Let's do that. Save the clutter. Square root 9 minus x squared. What in the world is this? Well, the 1/2 cancels the 2. The minus squared goes away because minus times minus. And so I'm just squaring x times 1 over square root 9 minus x squared. You can put the minus in here too. I guess it doesn't hurt. But that's what we're squaring. The minus doesn't cancel right away. It cancels the square. So we're squaring this, and we get x squared over 9 minus x squared. Square root, oops, plus 1, sorry. Square root of 1 plus this right here is x squared over 9 minus x squared. There it is. That's what I have to integrate. This is 1 plus, here's f prime squared. Here's 2 pi f. And that'll give me the surface area of the revolved orange slice. Again, these things are supposed to improve your integration skills. It's not a bad idea necessarily to use Symbol Lab and try and check these things. It'll show you the steps and you'll probably learn something. But you should be able to do these things pretty quickly by hand also in this one. How can I do this one? This one's kind of tricky actually. Symbol Lab might have a problem with this. I don't think so. If I multiply this square root in here, then I get square root of 1 times 9 minus x squared plus x squared over 9 minus x squared times 9 minus x squared dx. There it is. I just multiply square root of 9 minus x squared. Right? The square product of the square roots is the square root of the product. Is what I've done there. So this is 2 pi integral 0 to 1 square root 9 minus x squared. And now these cancel. So I get plus x squared. And that makes these cancel. Well, square root of 9 is 3. That's easy. 2 pi times 3, the square root of 9. Integral from 0 to 1 dx. I gave you a cooked problem. This is just x evaluate 1 and 0 and take the difference. This is equal to 1. So we've got 6 pi answer for this one. That's the surface area for this problem. Comments? Well, we had a problem kind of like this on the last test. Hopefully everybody has figured it out since then. I sent the test back. Don't forget the key is online if you ever want to pull it down and look at what I did on those things. I like to go over those in class, but it just doesn't seem the same when it's not in person. I haven't been doing that this semester. Find exactly, let's just say evaluate, the hyperbolic trig function 10 of the natural log of 2 by hand. You can try this, your calculator or one of these online programs might do it. But this is pretty easy by hand. Remember 10? What you need to remember about these hyperbolic trig functions, these are used a lot, and then the other ones, the inverses, are not used so much. Just remember the inverses can be written in terms of logarithms that you can look up if you need them. But since in cost you should have memorized, they're easy. They're just e to the x minus e to the minus x over 2. And e to the x plus e to the minus x over 2. Those are the hyperbolic trig functions, we call them. So we give a notation similar to the circular trig functions, sine and cosine. And now the tangent must be the quotient of those. The 2's canceling. We've got e to the x minus e to the minus x over e to the x plus e to the minus x. This is the hyperbolic tangent, is sinh over cos, hyperbolic sine over hyperbolic cosine, with the 2's canceling. So if you don't remember tangent, you can figure it out by taking the quotient of these two. That's what I used to do at least. Still think of it that way. But anyway, now what goes in here instead of x, since I'm not taking hyperbolic tangent of x, but hyperbolic tangent of ln2 is ln of 2 in every parenthesis. There's hyperbolic tangent of ln2 instead of x. Well, what's e to the ln2? They undo each other. You get 2, right? Over here, what do I do with this one? Well, I treat this as e to the ln of 2 to the minus 1. I put the minus 1 up in the power. And e to the ln2 is 2 again. And e to the minus ln2, I write that as e to the ln of 2 to the minus 1. So this is 2, and then e and ln cancel each other. I just get 2 to the minus 1, or a half. And at the bottom, I've got 2 plus also a half. So let's say it's 3 halves on top, divided by 5 halves on the bottom. The 2's canceling. I've got 3/5. When you take the hyperbolic trig functions of a logarithm, it tends to simplify. The moral of that story. All right. Look at the next one here. Evaluate the integral by making an appropriate substitution. X squared e to the minus 2x cubed. With respect to x. This one is supposed to make you memorize the integral of the exponential function, which is new this semester, right? Because actually, once you make this substitution, it's pretty easy. Other than that, it's all old material. Again, I think of a substitution because I have e to the mass. I think, what would happen if I let u be the mass? Then it's just e to the u. That makes it easier. But if I'm going to do that, then I have to get rid of dx in favor of du, which is du dx, derivative of du dx. Well, du dx is minus 6x. Oh, I don't have minus 6x. Let's see. Minus 6x squared, excuse me. Well, I almost have it. I have x squared. If I get this to within a constant, I can always just do this, multiply both sides by minus 6, and say minus a 6 du can replace x squared dx that I do have. So I'll take x squared dx, scratch it out, substitution, put in minus a 6 du. Right? Then I'll take the minus 2x cubed and scratch it out and put u. This whole integral becomes e to the u times minus a 6 du. Or minus a 6 integral e to the u du. Well, the exponential function is new this semester, but it's the easiest one of all. It's its own integral, right? So the integral of e to the u is e to the u plus an arbitrary constant. The constant technically multiplies a 6, but a 6 times a minus a 6. The minus a 6 times an arbitrary constant is an arbitrary constant. So I'll just put the c like that. Now I'll put back what u is. This is minus a sixth e to the minus 2x cubed plus c. There's the answer to that one. No, these aren't too bad, huh? You just have to remember how to integrate exponentials, and then also the other functions we did, inverse trig functions, logarithms. We did a lot of functions this semester. This one, more than any other semester in the calculus sequence, requires doing lots of integrals, and so it helps you a lot to have a calculator with a computer algebra system or online ability for the final exam, so you can check all these things. Isn't it nice? You can go check out your answers on all those ones that are just integrals. So that's not too bad. Find dy dx if y is sinh of x squared over 2. You didn't get the chain rule down before, you have to now. X squared over 2, sorry. Well, this is what you do if you have derivative of a function of x, then it's a chain rule, right? You can say this is d sinh u dx, right, where u equals 1/2 x squared. But by the chain rule, this is d sinh u dx like this with du's in between, right? D sinh u du dx. Then you have to memorize, this is a new function we did the derivative of this semester. Derivative of sinh is cos. And then du dx, if u is x squared over 2, is x. So my result is x cos x squared over 2. Easy, huh? Just have to remember the chain rule and the new rules for taking derivatives of these hyperbolic trig functions. Let's try number 7. Number 7 says to evaluate all these integrals. And there's other kinds of integrals too, but mostly I need to stick to the kinds that are like this since that's make this similar to practice tests. But if you have a power of one trig function and a power of another function, trig function multiplied together, this is the kind of integral that comes up a lot in practice. Partly because of our substitution methods for other integrals, but also they come up in their own right. Let's see. Pi over 4, yeah. Sine cubed 2x, cosine fifth 2x. What in the world am I going to do that if I get that, with that if I get that on the test? I have to switch to my fluorescent orange here. All right. Well, when you have an integral, this is to memorize, sine nth power of u, cosine nth power of u du. If m is odd, you can let u be the other one. Cosine. If n is odd, you can let u be the other function sine. If they're both even, then you go to another trick. For instance, you can rewrite in terms of tangents and secants, and it works with a lot of effort. Or you can take one of these and write them as, like sine fourths, you could write as 1 minus sine squared, or 1 minus cosine squared, and then square that. You can do tricks like that and use the reduction formula too. So there's different ways, but if one of them is odd, this is typically the way you attack one of these kind of problems. And similarly, if it's tangent and secant or cotangent and cosecant, same thing, except if you have one of those, then you want one of them to be even and the other one to be odd. If I have tangent u times secant u, each to a different power. Now, if m is even, you can let u equal, if m is odd, you can let u equal secant, the other one. I put u, I better put w because I already wrote u, sorry. But this is the substitution you make. And if n is even, then you let w equal the other function tangent. And then similarly with cotangent, cosecant, same even amount there. All right, so this is the first case of powers of trig functions multiplied together. And there's one more trick. It doesn't matter whether they're both u or both x or whatever. Just think of u equals 2x to make the same substitution. So on this one, I'm going to let u, since the first power is odd, power of sine is odd, let's let u equal cosine. Right? Or w. And that will make this easier. If I do, then dw or du has to be, maybe I should use w since I did up there. dw has to be the derivative of this, dx. Derivative of cosine 2x, remember the chain rule for this is minus 2 sine 2x. That needs to multiply dx. So I have to pull one of these signs out to make this substitution. So I'll call this now sine squared 2x. Put a minus out here and then cancel with a minus in here. Let's see. In fact, let's do it this way. So the first thing I do is I rewrite this integral in a more appealing form for making the substitution. I need a minus 2 sine 2x dx. So I put it in there. I take one of these signs over to the end. I multiply by minus 2, and then I cancel minus 2 with a minus 1/2 outside. And I reduce the power here, so the sine times sine squared is sine cubed. So all I did was rewrite this one, pulling a minus 1/2 out of here. Now I've got it because cosine of the fifth of the substitution is u equals cosine is just w. Minus 2 sine 2x dx, I set it up, is dw. And what about sine squared? There's a problem. Well, by the substitution, it always leaves an even power on the last one. So this is 1 minus cosine squared w, which is also 1 minus cosine squared 2x, sorry, which is also 1 minus w squared. So the even power can be replaced using the Pythagorean identity. The sine squared is 1 minus cosine squared because sine squared plus cosine squared is 1. So I'll rewrite this now as 1 minus w squared. And this then is cosine is w, this is w to the fifth, and dw. This nasty integral converts into this simple integral of a polynomial. I can do this one. I do need to change the endpoints. Here, x went from 0 to pi over 4. I could put on here x equals 0 to pi over 4, or better yet, let's say when x equals 0, you get w equals cosine 0 is 1. When x equals pi over 4, you get cosine of pi over 2 is for w is 0. So it goes from 1 down to 0 instead of 0 up to pi over 4. So put this aside. Now, this is integral from 1 to 0 of w to the fifth minus w to the seventh. And I've got a minus here. This is minus 1/2 w to the sixth over 6 minus w to the eighth over 8. Plug in 1 and 0 and take the difference. See, I plug in 0 and I get nothing. Nothing minus nothing leaves nothing, right, as they say. And then plug in the bottom end point, I get 1/6 minus 1/8. So there it is. Well, this is 4/24 minus 3/24. This is 1/24. Minus a minus makes plus. A half of 1/24 is 1/48. There's the value of that integral. Minus a half of minus a 24th is plus 1/48. There's a challenging integration. How about integral of x squared over quantity x minus 2 squared? That was A. You know, there's a couple ways to do this one, actually. One of them is partial fractions. Another one is a substitution. Whenever you have a function of a function, here we have the square of the x minus 2 function. You might think, what if I let u equal the inside function, x minus 2? Then du would be du dx dx. Is 1 dx is just dx. So I can scratch out dx and just put du. If u is x minus 2, then x is u plus 2. And at the top, I could rewrite this as u plus 2 squared. And at the bottom, I've got u squared du. There it is. That's a lot easier. This one's just a straightforward substitution. Well, it's the integral of u squared plus 4u plus 4 all over u squared. Which means I have to integrate 1 plus 4u to the minus 1 plus 4u to the minus 2. But that's an easy polynomial. All right, integral of 1 is just u. Here's another one that we just wanted to specify. What's the integral of 1 over u? That's natural logarithm. So we got minus 4 plus 4 times integral of u to the minus 1 is natural logarithm. Actually, absolute value of u in case it's negative. And then plus 4u to the minus 2, the integral of u to the minus 2 is u to the minus 1 over minus 1. Like that. Then there's an arbitrary constant. So I write this out with u equals x minus 2 as x minus 2 plus 4 natural log absolute value of x minus 2 minus 4 over x minus 2 plus a constant. So there's 7p. And a lot of these, there's a hard way as well as an easy way. So the other way you could do it is partial fractions. This looks harder to me. We could say that this is integral of, and if we rewrite this, first we got to do a division. We got to take x squared minus 4x plus 4. Let's see. You know what? Let's see. I miswrote this. No, that's right. Okay. That's okay. Yeah. X squared minus 4x plus 4 is this denominator here. And if I divide the numerator x squared by that, let's say it goes in one time. Oops. And I get x squared minus 4x plus 4 subtracted from this one. Subtract the x squareds, they cancel. Subtract this one, I get plus 4x. Subtract this one, I get minus 4. And now that's the remainder, and this is the quotient. So I can rewrite x squared over x minus 2 squared as the quotient 1 plus the remainder 4x minus 4 all over the divisor, x squared minus 4x plus 4. That means I could rewrite this integral in the following fashion. I rewrite this as integral of 1 plus 4 times x minus 1. Well, let's leave it on there. 4x minus 4 over x squared minus 4x plus 4 dx. Put in the partial fractions representation. Now I have to rewrite this using partial fractions. This and I might give you partial fractions on the test. Certainly, that's one of the methods we have here. This is supposed to be, well, since the bottom is actually x minus 2 squared, I've run it as far as I can already. Right? The partial fraction says I write this as a over x minus 2 plus b over x minus 2 squared, but that's what I already have. So what that tells me is I actually have to be able to do this now without using partial fractions to simplify it. It would just give me the same thing back. But I can do this. I can rewrite this as integral of 1 plus, and now what I do is I try and put the derivative of the bottom on the top here, derivative a multiple of it. Derivative of the bottom is 2x minus 4. So I want the top to be a multiple of that. Let's call this 4x minus 8 plus 4. Let's write it like that. Then you see in the next step what I'm doing. All right, so I'll write 4x minus 4 is 4x minus 8 plus 4. Now this part here is the derivative of the bottom times 2. So I'll rewrite it like that. All right, 4 over, this is x minus 2 squared. 2x minus 4 times 2 gives 4x minus 8, or x squared minus 4x plus 4, and then the 1 hangs out there. And so this one comes down here. Now we can do this. We can make a substitution here. U equals x squared minus 4x plus 4. And du is then 2x minus 4 dx. Derivative of dx is the numerator, right? Without the 2. So I have integral 1 dx plus twice this integral, 1, well, du over u. Hate that when I sinus it back up. Du over u. And then this one will be 4 times the integral 1 over, let's call it w squared dw. And this one I make a substitution. W equals x minus 2. dw equals dx. So integral of 1 is x plus twice natural logarithm absolute value of u minus 4 over w, right? Integral of w to the minus 2 minus w to minus 1 over minus 1. And then there's plus c tagging on the end. Don't forget the plus c. If you do that in every problem on the test, you probably 10 problems, you probably lose 10 points. Don't want to do that. All right, so x plus twice natural log u was x squared minus 4x plus 4. Well, wait a minute. That was x minus 2 squared. And I can drop the absolute value since it's a square, it won't be negative. Then minus 4 over w, where w is x minus 2. plus a constant. I can pull the power down and say this is actually x plus 4 times natural log x minus 2. Now I need the absolute value back though. Minus 4 over x minus 2. Plus a constant. There's a good way to write that integration. Hope that looks like what we had. It's been so long I can't remember. But there is an example of quotients of polynomials. If the power on top is at least the degree of the power on the bottom, then you first have to do long division to pull out the quotient, and then write remainder over divisor so that the top is a lower power than the bottom. Then you can apply partial fractions, or this trick here where you write a derivative of the bottom and what's left over the bottom and can integrate it that way. All right, we've got another one coming up. X squared over square root x squared minus 4. Let's try that one. How would I do that one? This one has another trick. I'll give you a different integral on the test, but it'll have the same trick. Remember how to do this one? When you see square root x squared minus a squared in an integral, one thing to try, sometimes it helps, sometimes it doesn't, is letting x equal a secant theta or cosecant theta, where a cosecant theta works just as well, and make a triangle. That really helps on these. After all, if I let x equal a secant theta, in this case, I'm going to let x equal 2 secant theta. Remember what the other cases were? If you had square root a squared minus x squared, then you try x equals a sine theta, or cosine theta works just as well. If you have square root of x squared plus a squared, you try x equals a tangent theta, or cotangent, doesn't matter. So those are the substitutions. We want to do this one. Well, if x equals 2 secant theta, dx has to be the derivative thereof. D theta. Minus dx d theta d theta. So the derivative of secant theta is secant tangent. And then I also need to get rid of that square root, but here's where the triangle shines, right? You don't have to draw it accurately. Just make it so that in a right triangle, x is 2 secant theta. So if I put theta here, let's say, this one says equivalently secant theta equals x over 2, but that's supposed to be hypotenuse over adjacent. So I put the hypotenuse x and the adjacent 2, and that works. Or you put 4x and 8, just so the ratio is x over 2. And then on this triangle thing, the trick is to calculate the other side, because that's what makes the triangle useful. The other side by the Pythagorean term becomes the square root that you see, right? This is square root of hypotenuse squared minus the other leg squared is square root x squared minus 4 that we have in the integral there. That being the case, we can now say this over this has a nice relationship. From the triangle, we notice that, let's see, tangent theta is opposite over adjacent is square root x squared minus 4 over 2. Consequently, 2 tangent theta can replace the square root that we see. Alternatively, you can use the Pythagorean identity and say 4 secant squared minus 4 is 4 tangent squared. But we'll say this is square root of x squared minus 4. So the square root can come out in favor of 2 tangent theta. Now I put that in. This is 2 tangent theta. But it's just a clever substitution, right? X squared. X is 2 secant theta. So this is 4 secant squared theta. And dx, we said, is 2 tangent theta secant theta. D theta. Now I've got it. The tangents cancel. The 2's cancel. And I've got integral 4 secant squared here. This is all gone. Secant theta d theta. So this is 4 times the integral of secant cubed. This one poses a problem. If power of secant is even, you can let u equal tangent, but it's not. Power of tangent is odd, you can let u equal secant, but it's not. So we're kind of stuck here. How can we possibly do this one? We could convert it to a cosine problem and call this 4 integral 1 over cosine cubed. Theta d theta is one way. Or you can use the reduction formula for secant, which is actually hard to come by. I'm trying to think if this is the best way to do this one. Now you can think of this as a power of cosine times a power of sine, right? This is cosine to the minus 3, sine to the 0. And it's an even power of sine, but it's an odd power of cosine. So I'd suggest letting, when the power of cosine is odd, letting u equal sine. Then I get du is derivative of u d theta is cosine theta d theta. Right? Well, I don't have a cosine theta d theta, so I use Howell's rule. I stick it in here. 4 integral of 1 over cosine 4th theta times cosine theta d theta. All right, so that's 1 over cosine cubed. But now this becomes du. This becomes, let's see, it's going to be tricky, isn't it? 4 integral. Cosine squared is 1 minus u squared. Right? But cosine squared is theta is 1 minus sine squared theta is 1 minus u squared. So cosine of the 4th is 1 minus u squared squared. And now I've converted it to this integral. This one can be done by partial fractions now, but it's not easy. Now let's go on. I guess I'll have to erase the triangle here. There's a question, let me know now so I don't erase it. All right, now you're down to partial fractions. You can write this as 4 times the integral of 1 over 1 minus u squared times 1 plus u squared du, right? So this has a partial fractions decomposition as a over 1 minus u plus b over 1 minus u squared plus c over 1 plus u plus d over 1 plus u squared. And you can try and find the 4 letters here. This is one way to do it. But this is one of the more difficult ones on the whole test, right? Now multiply through, if these are supposed to be equal, multiply through by the largest denominator here and get 1 on the left, equals this times 3 of the factors here, a times 1 minus u, 1 plus u squared, plus b times 1 plus u squared, plus c times the 1 minus u cancels, 1 plus u cancels 1 and you get 1 minus u squared, 1 plus u, plus d times 1 minus u squared. But the point is, when you see this square root x squared plus a squared, x squared minus a squared, or a squared minus x squared, you can try one of these three substitutions. There are also some inverse, or there's also some hyperbolic trig substitutions that work for some of these. But you don't need to memorize those for the test. Sometimes they make this a little simpler, but don't solve new problems. But, all right, so now I've got 1 equals a times, let's see, 1 minus u times 1 plus 2u plus u squared gives me 1 plus 2u minus u is plus u, plus u squared minus 2u squared is minus u squared, and then minus u cubed. So there's a, then b multiplying that out, u squared plus 2u plus 1, c multiplying that out, u plus 1 times 1 minus 2u plus u squared gives u cubed plus u squared minus 2u squared is minus u squared. Plus minus 2u plus u is minus u, and then plus 1. That's what c multiplies. And then finally d multiplies 1 minus 2u plus u squared. And then from the other side, I carry the 1 over, 0 on this side, and minus 1 on this side. There it is. Well, that's pretty hard integral. I think one of those hyperbolic trig function substitutions actually would have been easier. But now you set the coefficients of each power of u equal to 0. You've got 0 equals u cubed multiplies minus a plus c, so it's c minus a. U squared multiplies minus a plus b minus c plus d. U multiplies a plus 2b minus c minus 2d. And then finally, the constant terms are a plus b plus c plus d minus 1. And now I can find all those different coefficients. Now you have a system of 4 equations and 4 unknowns to solve. Right here. 2d. All right. Well, this isn't even an easy system of equations. I don't think I'll give you one with constants quite that hard. I'll say you go ahead and figure those constants and integrate them. This is a system of 4 linear equations. You can immediately, for instance, from this one deduce that a equals c and plug it in here. This one becomes, or c equals a, let's put instead. And then, but b minus a plus d equals 0. I guess this becomes b minus 2a plus d equals 0. Each of these coefficients has to be 0 in order for this to vanish for all u or in any interval. This one with a equals c, well, the a and the c cancel, and you've got 2b minus 2d equals 0. And then this one says 2a plus b plus d equals 0. That's a equals c. And now this one says that b equals d. If b equals d, I can put that up here. And this system becomes, well, the b and the d cancel, and I've got a equals 0. Right, if b equals d, oops, no, it's minus d, I'm sorry. That's 2b minus 2a equals 0. By replacing d with b, it becomes 2b minus 2a equals 0. This one we're done with, b equals d. This one, putting in b equals d, I've got 2a plus 2b equals 0. All right. Oh, except I'm not done. This was not equal to 0. This is equal to 1 here. 2a plus b plus d equals 1. So this one equals 1. So evidently I have b equals d, c equals a. This one says b equals a. So a, b, and let's see. A, b, and c are all equal. And b is equal. All 4 of these are equal. And 2a plus 2b equals 1 says a equals a quarter. And b equals a quarter. So I deduce from all those equations, right? So 2 times a quarter plus 2 times a quarter is 1. And then all these equations say their others are equal, give you that. So evidently I have that this is 4 times the integral of a quarter over 1 minus u plus a quarter over 1 minus u squared plus a quarter over 1 plus u plus a quarter over 1 plus u squared du. Well, the 1/4 and the 4 cancel. Integral of 1 over 1 minus u is actually minus natural log absolute value of u minus 1 by substitution, w equals 1 minus u. This one, the 4 and the 1/4 canceling becomes 1 over 1 minus u. This one becomes ln u plus 1. This one becomes 1 over minus 1 over u plus 1. Then there's a constant. And let's see, then I got to go back and put in what u is. So finish all this up. U is equal to, I've erased it, secant theta, 2 secant theta. So this is the answer with u equals 2 secant theta. I think there's a shorter answer. I think I did it a different way when I first put the key up. So anyway you want to look at it, this is the usual substitution when you see that square root with the point. I don't want to take too much time with this. But put back u equals secant theta, and then secant theta in turn had a substitution, 2 secant theta, I think it was, to get back to x. I put you all to sleep on that one, sorry about that. Here's another one. I've tried to put a big smattering of different kinds of things on here. Suppose I look at 7d, integral of x squared sine 2x dx. How can I do that one? Maybe you remember when you have a small power of x times an exponential or a trig function or a hyperbolic trig function equal, even. The trick is to use integration by parts. Let u be the small power of x, and let dv be everything else, and that will give me a new integral where the power is reduced. Does that sound familiar? So I let u equal this and dv equals this, then du is the derivative of this dx, is 2x dx. But v is the integral of this one, is minus a half cosine 2x. And you leave the constant off on integration by parts. This has to come out uv minus integral v du. This is, to me, one of the most common methods after substitution, probably the most common after substitution. So expect something on integration by parts on the test. Have that uv minus integral v du formula memorized. This is then x squared times minus a half cosine 2x, there's uv, minus integral v, which is minus a half cosine 2x, du is 2x dx. And sure enough, it's x to the first power. Well, the 1/2 and the 2 also cancel by luck, and the 2 minuses cancel. So this whole thing just becomes the integral of x cosine 2x dx. Right? So I'm going to say this one is minus a half x squared cosine 2x, the first term here, plus this integral. How do I do this one? Small power of x times a trig function. I let u be x and dv be the rest with dx. Do a second integration by parts. So that's uv minus integral v du for this one. Here's u, so du is dx. And v is the integral of cosine 2x, is 1/2 sine 2x. Evidently what I've got is minus x squared over 2 cosine 2x. By the way, since I'm leaving you a little extra time on this test, I want to make sure to make this about the same as the midterms, like an hour, hour and a quarter to finish it, so you can check all your answers. Do go back and check your answers. A lot of these, like when I get it, doing integration, I can try taking the derivative and see if I get the integral back that I have. That'll verify that I got this right. So here's what I have here. U is x. V is 1/2 sine 2x. From that, I subtract integral v, 1/2 sine 2x. Du is dx. Well, this integral, you recall, is just minus 1/4 cosine 2x plus a constant. When I drop the last integral sign, I should put my plus c. And it's subtracted, so I get plus 1/4 cosine 2x. My result then is minus x squared over 2 cosine 2x plus x over 2 sine 2x plus, the minus is canceling, 1/4 cosine 2x plus a constant. Here's when you have a small power of x multiplying one of those functions. What about the integral of the natural logarithm? Well, I'm trying to get you so you remember a lot of these tricks here. When you see this, do that. When you see that, do this, right? It's like a cookbook. If I see an integral like 7e that has a logarithm or an inverse trig function, what do I think? Anybody remember? I think integration by parts. So these are also, when I have logarithms, inverse trig functions, sometimes that works. If it's just plain logarithm and inverse trig function, it always works. So I'm going to, there's no point letting this be part of dv. I can't integrate it to get v or I'd be done. So I have to let this be u and then this must be dv. Tells me that du is the derivative of the logarithm of dx is 1/x dx, and v is the integral dx is x. So this is uv minus the integral v du. And let's see, uv is x ln of x minus the integral of v is x. Du is 1 over x dx. Oh, this is just the integral of 1. That's x. So this is x natural log x minus x, and then they drop the last integral, but plus c. There's 7e. Not so bad. Getting a little easier for me. Any requests yet? I don't know if you're looking at any of these. I think I'm supposed to put up a lecture or two from last week, too. I was trying to get out, and I haven't got that out yet. So I'll see if I can get the last lecture or two, if I can still have those online here. I know it was asked for. 7f asked me to integrate x squared over square root 4 minus x squared dx. Oh, once again, a square root, but this time it's a squared minus x squared instead of x squared minus a squared. What was the substitution for that one? I think of this as 2 squared. The substitution is x equals 2 sine theta this time instead of secant. Right? So if it's a squared minus x squared, you let x equal a sine theta. That substitution would require dx equal to cosine theta d theta, right? The derivative d theta. Then I draw the triangle. In it, I want to choose theta such that x is 2 sine theta. Well, that means that sine theta is x over 2. So I put opposite x and hypotenuse 2 this time. Then the last leg is square root 2 squared minus x squared, the very square root I see in there, right? That means I'm on the right track. So now I can figure that the cosine of theta must be adjacent over hypotenuse. Actually, let's do secant. We can use cosine or secant, but let's say secant. That's the square roots in the bottom there. No, let's do one. Let's just do cosine. Never mind. Because I've already got sines and cosines here. Cosine theta will be this over this is square root 4 minus x squared all over 2. Says that square root 4 minus x squared can be replaced with 2 cosine theta. So see how nice the triangle is. Now, this square root replaces with 2 cosine theta. X squared replaces with this squared is 4 sine squared theta. And dx replaces with 2 cosine theta d theta. There's the substitution. It'll get rid of that nasty square root, right? Well, luckily, cosine theta, 2 cosine theta on the top and 2 cosine theta on the bottom cancel. And I'm just integrating 4 sine squared theta d theta. That's it. We can do this one. The reduction formula actually does apply if you like the reduction formula. Look it up in the book. I don't tend to memorize that one. It's not used that often. But remember, when you just have a trig function squared, you use a half angle identity like that. I can rewrite this. I recall from the half angle identity that sine theta is plus or minus square root 1 minus cosine 2 theta over 2. So sine squared there, I can rewrite as this squared is 1 minus cosine 2 theta over 2. And that's an easy way to integrate sine squared. It's similar for cosine squared, you just get a plus here. So in the other case, cosine theta is plus or minus square root 1 plus cosine 2 theta over 2 is its half angle identity. So we'll use this one. Well, this is twice the integral of 1 minus cosine 2 theta. Oh, I should have left it here maybe, huh? Oh well. D theta is twice. Integral of 1 is theta. Integral minus cosine 2 theta is minus a half sine 2 theta. And then there's an arbitrary constant added on. So I say it's 2 theta minus sine 2 theta plus a constant. There's the answer to 7f. Oh, it looks like I'm about out of time. Well, we got just about through all the integrals. There's one partial fractions left that has an improper integral. And then there's number 8 also. Think if there's any other problems, you see, I guess 8 through 12 still left. You want to look at for next time, feel free to send me text messages, and we'll pick these up where we left off. Any last minute questions? Okay, you'll have a nice rest of your evening.
Thank you.
Thank you.
All right, thank you.
Thank you.
Thank you.